to another tutorial. My name is Tanmay Bakshi, and this time we're going to be going over how you can use convolutional neural networks with Keras in Python in order to create an MNIST digit classifier. And now let's get into how we're going to be doing that. Alright, so to begin today, what we're going to be doing is we're going to be, first of all, I assume that you have Keras and TensorFlow installed on your system, and today we're going to be using Ubuntu 14.04 to use Python, and specifically the Keras library, in order to train convolutional neural networks. And in this case, we are going to be training a CNN on the MNIST data that is available online. Alright, so let's begin. Now, most MNIST digit classifiers built with convolutional neural networks use, standard architectures like LayNet, created by Yann LeCun. There will be a link to that in the description, who is actually the creator of the data as well. But the only thing is, though, I didn't want to use one of those architectures. I wanted to use a custom architecture, and so I built this, I guess you could say, sort of mini convolutional neural network that can actually be trained. You can actually train this at home on the MNIST data, and now let's get into how this works. So to begin, just in case you're not familiar with the MNIST data, well, here's a quick overview. So the MNIST data is actually this huge data set of images, and these images actually represent digits that have been drawn out and handwritten by people. Now these are all 28 by 28 black and white photos, and so, like, for example, we've got classes 0, they're handwritten zeros, 1s, 2s, 3s, 4s, 5s, 6s, 7s, 8s, and 9s. So we've got 10 different digits that have been handwritten out a lot of different times by people, actually, and those have been put into our data set. Specifically, each number on average has been written, or we have handwritten images of 6,000 of each. So we've got 6,000, and these will actually be for our training set. But for our test set, we've got an additional 1,000 images that we can then go ahead and test and validate with to ensure that our training is going nicely and get a good measure of accuracy without having accuracy on an overfitted neural network. Alright, so now since we've gotten 10 different classes, each one containing 6,000 train, 1,000 test, in total we've got 60,000 different train images. And then, of course, we've got 10,000 different test images. And that is what we're going to be training our convolutional neural network on. But before we actually get into the code of this and how it really works, I'd like to go over the actual convolutional neural network architecture a little bit beforehand. So let's actually draw out what this convolutional neural network is going to look like. Now, I assume that you already know what convolutional neural networks are and the different types of layers they provide and the activation functions, etc. But in case you're not, there is going to be another video coming out very soon describing all the different types of layers with convolutional neural networks, how they work, and the logic behind them. Again, coming out soon, but for now, let's talk a little bit about what's going behind it. So it actually begins with one convolution layer. So we begin with this convolution layer, and this convolution layer actually has 16 filters and a 5 by 5 filter size. Now, after this convolution, we are going to have an activation function, and this activation function, in this case, is going to be the rectified linear unit activation function. Again, in the second part that's going to be coming out soon, I will discuss why exactly rectified linear units are used so much with convolutional neural networks, and why you don't usually see them in other neural network types, or regular activation functions that are used more often with convolutional neural networks. Alright, so after our activation function, we're going to make our image much smaller by doing something called max pooling. So of course we're going to have a max pooling layer. And so here we've got a 5 by 5 size. And after that, we practically just repeat the cycle. We have one more convolution layer. And this now has 32 filters. Again, what happens is as you go deeper in the neural network, you usually start to see more and more filters coming along so it can learn more and more sophisticated different types of features. After that, again, this is a 5x5 filter size. And once we've got that done, we of course send it through an activation function, such as rectify linear unit once more. And then of course we do one more round of max pooling. Once more, 5x5, and once that is done, we are ready to flatten the data, meaning it goes from 2D to 1D, flattening. It goes from a 2D array, two-dimensional vectors, to just one-dimensional array. And that one-dimensional array is then used by a pretty much classic feed-forward multi-layer perceptron neural network, which will then be able to classify what this image is. So like now what we're going to do is we're going to have something that convolutional neural networks like to call a fully connected layer. And so this fully connected layer will have 1,000 output neurons. And what's going to happen is we're going to use the rectified linear unit activation function once more. Once that's done, we're going to have one last fully connected layer. And this will finally have just 10 outputs. And this is going to be our final, I guess you could say, probability matrix. In fact, that is what it's called. And that's why we're using for this the softmax activation function. The softmax activation function is then going to basically take these 10 outputs and create this probability matrix for each digit individually. So what's going to happen is, let's just say you feed in a 2. The 0, 1, 2th element of the array, meaning technically if you were to start from 1 to 3rd element, if you were to start from 0 to 2nd element of the array at the output, would have a higher number than the rest. And that would indicate the probability percentage, the percentage of likelihood basically, that the convolutional neural network believes that this digit is in fact this output. And so I will explain a little bit more and make that a little bit more clear in the coding part, but just before we go, one more thing I'd like to mention here is that I was actually able to train this neural network, and the great news is that I was able to achieve an absolutely great 99.66% accuracy. So that's actually a great percentage for such a small neural network. Usually you've got much deeper neural networks with more filters, and of course then they're able to achieve such accuracy. But with just 4 epochs and only around 7 minutes of training, we were able to achieve 99.66% accuracy. So if we were to make this deeper or generally optimize this architecture, and if we were to train it for a bit longer, we could of course crank out some more accuracy and get it as accurate as possible. But I found that this is still very, very accurate, and I was able to test it out on many test images and getting almost every single one of them correct. In fact, it believes that each of these, whenever I give it an image, it believes so much in its answer that it has so many 9s that it just rounds it to 100% confidence most of the time. And that's what you're going to be seeing now, how we can use this in Keras and Python on an Ubuntu machine. Now, one thing I'd like you to note is that this example is using CUDA for GPU acceleration, as well as CUDNN for more further acceleration with TensorFlow and Keras. So if you'd like to train this on your CPU, since this isn't too much of an intensive neural network, it would still work on a CPU or an OpenCL supporting GPU. It's just that with NVIDIA GPUs, you get that really fast performance because of CUDA and all of the optimization provides. So I'd highly recommend doing this sort of training on an NVIDIA GPU due to the massive number of, the millions of things that you can do at once with a GPU. But now let's get over to the machine, where I'm going to be showing you now how you can actually train this convolutional neural network. Let's get to it now. Alright, so welcome back to the coding part, and now I'm going to be showing you how you can actually implement this MNIST digit classifier using Keras in Python. Alright, so let's head over to an SSH session I've got running here. As you can see, I've basically SSH'd into a server that will allow me to do all of this deep learning stuff. So now let's go ahead and begin. Now let's actually start off with the script that is going to be training training the neural network. But just before we even get to that, let's take a quick look at our data. Now if I go into the data and I go into the train directory, as you can see, we've got 10 directories under that, 0 through 9. If I go into 3, for example, as you can see, we've got a good 6,000 images that LS has printed out here. I'm not going to go through all of them though. And if we go back, as you can see, if we go to something like 8, we've got similarly 6,000 images for 8 as well. Then we can go back and really do that for whichever number we want. But then again, we can go over to our validation set or our testing set. And again, here as well, we've got 10 directories, and we can go into one of them like 6. And here we've got only 1,000 of those images, but still more than enough to test with for now. And so from here, we should be able to actually train our convolutional neural network and then actually use it using these validation images. Now, if we go back though, as you can see, if I nano this Python file, this is the file that's actually going to be helping us train our convolutional neural network. Now, we've only got a few inputs here. We're importing the image data generated from Keras, the sequential model, the convolution 2D and max pooling 2D layers from Keras, and of course the flatten and dense layers from Keras as well. Once the imports are done, we are then setting our image width and height, telling it where to find the train data and where to find the validation data, and finally how many training samples to use and how many validation samples to use. After that, I tell it that we're going to be training for 4 epochs, and once I tell it that, we start actually defining our model. Now, the model is, in this case, a sequential model, and what we're going to do is we're going to add our first layer, which is a convolution 2D layer with 16 filters, a 5x5 filter size, a rectify linear unit activation function, and a very simple input shape, which is the image width, the image height, and 3 channels. Once that is done, we have a 2x2 max pooling 2D layer, and after that, we've got another 5x5 filter size 32 filter convolution 2D layer, once again with the rectify linear unit activation function, which is then followed up by a 2x2 max pooling 2D, and that's really all there is to the convolutional part of the network. Then we've got our regular fully connected, or in this case dense layers, and so basically first of all we're adding a flattening layer, which will bring it from 2 dimensions to 1 dimension, and once we've gotten that data in 1 dimension, we're ready to actually use our fully connected layers, or again in this case our dense layers. Now our dense layers will really take whatever input size has been given to them, and they will output though 1,000 neurons. And again, rectify linear unit activation function will of course activate all of that data for us. And then finally, once we've got all of that data, we can then convert down onto 10 different classes with the softmax activation function in order to get that really great probability matrix, which will give us a percentage of confidence with every classification it creates. And once it is done, we then print out a model summary, which will basically just show us what the model looks like, so we're able to confirm that this is exactly what we want. We don't really use it for much though. We just use it to see what our model looks like. After that, then we compile this model, and basically what this is doing is it's getting it ready for training by giving it some parameters. For example, for loss, we're using the binary cross entropy algorithm, we are using the optimizer RMS prop, and for the metrics, we are keeping accuracy. But then, after we have compiled our model, we're creating a data generator for the training set, and this is where we do a little bit of data augmentation. We tell it how much we can rescale our image, how much to do the shear range with, and how much to do the zoom range with. Of course, we're telling it that it can do horizontal flips, that's why we're giving it true. But with the testing data generator, all we're doing is we're telling it that it can rescale. Again, we're giving it how much we believe it should be rescaling. Once that is done, though, we are creating a train generator, and in this generator, we are basically going to be passing it the data directory. We're going to be passing it the target size, how big these images are going to be. We're going to pass it a batch size for the training, and we're going to tell it that we're not using binary class mode. We're not using any of that. We're using the categorical class mode in order to allow us to have all of these different classes from 0 to 9. We're doing practically the exact same thing with the validation generator, and once we've got all of those generators down, then we can actually tell our model to fit towards a generator. We then pass it our train generator, tell it how many samples we're going to be using per epoch. We're going to be telling it which epochs to use here. We're going to be giving it the validation generator as well. And then finally, we're going to be giving it the validation samples as well to give it all the parameters that it needs in order to actually run the training. Once it is done the training, though, so this is a synchronous operation, so once it's done, it will save its weights to a file called MNIST neuralnet.h5. Now what we can do is we can get out of Nano and actually run this custom train script using Python. As you can see, what's happening now is it is training our neural network and that accuracy is going up. So what's happening here is it gives us our estimated time of arrival, and this will basically allow us to train our neural network. And remember, this is only going to do 4 of these sorts of iterations, and so of course you'd want to do as many as you can. Then again, you don't want to overfit, so it really depends on how deep your neural network is, how much data you have, and what sort of the ratio of split is between your training and testing set. It depends on a lot of different parameters, but again, you always want to pick and choose, and you always want to experiment until you find what works best for you and your specific neural network. Alright, so since I've already got this neural network trained, and it does take a little bit of time, again, because it's not this data set isn't massive, but it's not small either, so it wouldn't be very quick. So this is why I'd always recommend training on a GPU instead of, especially with convolutional and deep neural networks. But now what I'm going to do is I'm going to stop this training script, and now that that's done, let's just pretend, it's trained, and we've got our neural network file over here. Now we're ready to actually use this neural network and run predictions against it using our images. And the way we're going to be doing this is through another file called predict.py. Now inside of predict.py, we are importing NumPy, we are importing OpenCV2, we're importing all of the same Keras modules that you were just seeing, and of course we're importing the sys or system module. I'll tell you why in just a moment. Then, of course, we are setting the image width and height to 28 and 28 once more, just as we do for all of our MNIST data, because MNIST images are always 28 by 28 pixels wide and high. Then what we do is we create a function called createModel. We define this function, and what we're going to do is inside of this function, we are going to create a new variable called model, which is equal to a new sequential model, and then create the exact same model that we did in the training script, except that we're not going to tell it which weights to use just yet. We're going to print out another summary, and we're going to return this model. Then what we will do is we will actually open up an image using OpenCV. We will do image is equal to cv2.im read, meaning image read. And what we're going to do is instead of passing it a direct file path, we'll be sending to it the first argument sent to the Python script when you were running the script. And basically, in the first parameter, you are going to put the file path to an image that you would like to predict using this classifier. Once you pass that, then it will be opened, and CV2 will then resize it to 2828. This is not required because all MNIST digits are 28 by 28 by default, but if you would like to repurpose this to work with your own model or to work with your own data, then it's really easy to have this, because then you just set your image width and height up here, and it'll automatically change everywhere else to ensure that you are having your model work correctly. Alright, but after that, we are then calling that create model function that we have just created. And once we've got a model returned from there, we tell that model to load its weights from a file in the current directory called MNIST neuralnet.h5. And once we're done that, we are then ready to convert the image that we just imported using OpenCV2 and convert it to a NumPy array. And once we convert that to a NumPy array, we then reshape it to fit the image width, height, and then finally the dimensions, or not dimensions, the channels in the image, which in this case we are setting to 3 because our neural network was trained on 3 channels. And with 3 channels, you can always use RGB images as well as black and white. They both work. Although technically, since we're using black and white images, just one channel would work for the training and the testing and the predictions. But the thing is, if you want to repurpose this immediately, just get it working on your own data, which is RGB, then having 3 channels already there is really convenient. Alright, after that, we just add one more dimension to make this a 4th rank tensor with our NumPy array. And then finally, we tell our model to predict what it believes this image is by giving it the NumPy array and getting the 0th element from it. Now remember, this is a 2-dimensional array that NumPy is giving us. Like, for example, if we gave it an image of a 1, this would be our array. It would be 0, 1, 0, 0, 0, 0, 0, 0, 0. And so what's happening here is this is before the prediction. So what happens is this is a 2-dimensional array, but we get this first element, which is this first array, which in turn has 10 elements inside of it. And so what happens is we are able to get that 0th element, and then what happens is we have some logic to see which one has the highest probability. And so in order to do this, we find the best class and best confidence. Then we just do a really quick script here, which will try and see which prediction is the greatest. Once it has done that, though, then it will print out, I think this digit is A, then the best class, with, and then the percentage of confidence, and then confidence. So what this is going to do is if I just exit out of this script here, not exactly sure what I changed, but all right, let's go. And then what happens is basically we can run this Python script, Python predict, and then we can give it images that we want it to test on. Now the only thing is though, we're not going to be passing it training images because those images have already been well trained on. We're going to be giving it images from the validation set so that we are able to give it images that it's never seen before, therefore testing its true capability. The way we're going to do this is by going to the data directory, and inside of that we're going to go to the validation directory. Now these are all images that it has never seen before, and let's try out 0 first. We're going to try out all 0 to 9 and see how well it does. Now for the 0th, we can give it something like 701.png, again just random number, just throwing that out there. Click enter out, and as you can see, it says I think this digit is a 0 with 100% confidence. Again, that is absolutely great, but let's just see if it can classify a 1 with a good amount of accuracy. Let's just say 7014.png. Alright, so as you can see, this has correctly classified this digit as a 1 with 100% confidence, and so we are on the right track. So far, we're getting great accuracy. Let's hope we can keep that up. So now, again, we're going to try this out with a 2, and let's just say 2390.png. Alright, so as you can see, it's using our GPU to do this here. And as you can see, it says I think this digit is a 2 with 100% confidence, which again is the correct answer. Now let's try out what happens if we give it something like a 3. So let's give it a 3 this time. Let's just say, 5,000.png. Let's see what it says. As you can see, it says that I think this digit is a 3 with 100% confidence. Again, this is so close to 100% that it's just rounding up to 100% due to the fact that it is so sure that it's a 3. It's seen so many patterns in it that make it believe that it's a 3, that it's just not even going to give other classes a probability. And then what happens is, again, we can run this. Let's just try 4 now. For 4, we can use 5,000 for her. And as you can see, it says, I think this is a 4 with 100% confidence. Again, absolutely great. We can then go ahead and continue to say 5. where we can do, let's do 8,360.png or 60.png. Alright, so here we should be able to see that, apparently that image does not exist. Let's see. Yeah, sometimes, 66 works. Let's see. Alright, so I think this is a 5 with 100% confidence. Again, absolutely great. That is the correct answer, with a very good amount of confidence as well. We can go to 6 then. We can say 9,148 maybe. Let's see if this exists. Yeah, it exists. And as you can see, I believe this digit is a 6 with 100% confidence. Once more, we can then go ahead and give it a 7. And let's just say our 7 is 3,000 this time. 50 and 4. Hopefully that image exists, and it does, and as you can see, it says that 7 is the correct answer with 100% confidence. Now, once we're done 7, we finally have just 2 characters left to test. Our second last character is 8, and let's try 6024.png. Why not? Alright, so as you can see, again, it has classified the digit correctly with 100% confidence, and now we can go ahead and give it something like 9, and let's just change this up a bit. Let's just say something like 5029. Alright. And once more, it says that this is the correct, it says that this digit is 9 with 100% confidence, and that is once more the correct answer, and our users, and then again, I mean, users could have this built into their applications, because, like, let's just say you're creating a Node.js application or a website. You can use libraries that allow you to use Keras models in those languages, pre-trained Keras models in those languages, and you can have this convolutional neural network run in browsers, run on phones, run on desktop applications, really anywhere where a language that supports the device also has a library that supports pre-trained Keras models. As long as those prerequisites are met, you should technically be able to use this model anywhere. And again, in the worst case scenario, if you're unable to do that, then you can always just create a web API where you can send an image, it would send it back to the convolutional neural network, and the convolutional neural network would then go ahead and further return the answer, and then that would be replied to you by the REST API once more. Again, though, in part 2, there's going to be a lot more coming out in those terms, and so in part 2, you're going to be seeing a lot of how you can use these pre-trained models in many different languages. So that's all for this tutorial. I really do hope you enjoyed and you're able to learn how exactly you can use Keras in Python with a TensorFlow backend, and of course use it to train on your own data, really. And that's the best part. We're not using pre-built data sets. We're not using like cryptic data sets that are in random formats like LMDB. We're using actual image data, which sometimes, I guess you could say, isn't the best for performance. But then again, if you just want to get a convolutional neural network running quickly and running fast and running nicely, then of course images are always another option as well. Alright, so I really do hope you enjoyed. Thank you very much for watching today. That's going to be all for the video, and I really do hope you were able to learn from it. Again, if you did, please do make sure to leave a like down below, and of course share the video if you believe it could help anybody else you know, like your friends or family. And of course, if you have any questions or suggestions or feedback, please do make sure to leave it down in the comment section below. Email it to me at tadgymanny@gmail.com or tweet it to me at tadgymanny. Again, all contact information will be down in the description, as well as all of the code for this video. Alright, so if you really like my content though and you want to see a lot more of it, please do make sure to subscribe to my YouTube channel as well, as it really does help out a lot. And of course, finally, if you want to be notified through Google notification and email whenever I release new content, please do make sure to click the bell icon beside the subscribe button as well in order to be notified. Thank you very much for watching today. That's going to be all. Goodbye.